Meet the Texas Instruments MSPM0C1104, the world's smallest microcontroller, measuring just 1.6 times 0.86 millimeter, about the size of a grain of rice. But don't let this tiny size fool you. This MCU packs a punch. In today's video, we will explore what makes it special, design a PCB in KiCad, write firmware in Code Composer Studio, solder it to a custom board, and finally test it with some practical demos. Let's get started. The MSPM0C1104 is part of Texas Instruments MSPM0 series. It features a 32-bit ARM Cortex M0 Plus core running at 24 MHz with 16 kilobytes of flash and 1 kilobyte of SRAM. It's designed for low-power applications, making it ideal for wearables, IoT devices, and ultra-compact sensor applications. It also features GPIOs, ADCs, timers, and several interfaces like a UART, I2C, and SPI, all in this very tiny package. I'm very impressed with this small MCU, and I thought it could be very interesting to make my own board with this very special device. And it would also be a challenge to try and see if it would be possible to solder it to one of my own boards on my desk at home with only very primitive tools. But working with such a tiny package means no traditional pins. Instead, it uses a wafer-level chip scale package, which requires precise soldering and PCB design. So let's fire up KiCad and design a board for it. In the center of the design we have the MCU, so we have an 8-pin device, and you see the naming when we are talking about a BGA type. We have them renamed A1, B1, C1, D1, and on the other side A2, B2, C2, and D2. So we have 2 pins is necessary for the power supply, and then we have 6 pins for GPIO, and 2 of them are reserved in my design for SVD programming. Then we have 2 GPIOs here, and then we have 2 for a serial interface for the I2C port, and this is PA1 and PA0. And we see that PA1 is shared with the reset pin, and we have to have a pull-up resistor on this pin. And we are so fortunate that the SL pin is also pulled up here, so this should not be a problem, but more about that later. So we have a traditional LDO here. That's just a block terminal here where we can connect a 5-watt power supply, and then we have a regulated 3.3 volt over here. Then the MCU part with the decoupling capacitors. We have a green LED that indicates we have 3.3 volt power. Then we have a connector here. This is just a regular 2.54 millimeter spacing pin header where we have all the pins broken out. Then it's easy for us to measure if all pins are soldered correctly. And we can also connect miscellaneous DuPont connectors and so on if we want to play with some external signals. A few mounting holes, and on one of the GPIOs we have a LED, and then the I2C port is broken out on this quick connector here where we have 3.3 volt ground and then the I2C signals. So let's have a look on the PCB design itself. Here we have the final PCB design. This is just a very small board. It measures 30 by 30 millimeters, and it's a very simple 2-layer board. And I think we will just turn off the bottom silk layer and the bottom copper layer here. Then it's a bit easier to see what's going on. So we have the terminal block here where we connect our 5 volt. On the other side we have the quick connector with the I2C signals, and up here we have a 8-pin connector pin header where we have all the signals from the MCU, and we have a power LED, and down here we have the LDO that generates 3.3 volts for us, and then we have an LED connected to the PA24 pin of the MCU. And of course the center of attention here is U1, And you see I made a small cutout here in the copper pour so that we will not remove the heat from these very small pads here. Let's have a look on the footprint for the MCU. And it's here in the footprint designer. And we can see the small pads here, they only measure 0.2 millimeters each. And we can see that the solder marks expansion is only 0.05 millimeters. And we can just check the distance between each pad here. Let's try and inspect measurement tool. And here we can measure the distance between every pad is 0.35 millimeters. All right. And we can also have a look on the 3D model here. So this is just a very small package. Let's head back to the design here. We can have a view on the 3D model of the whole design here. Let's just enable our silk screen for the bottom and the bottom layer, and then go to view, 3D viewer. And here we have the 3D design. And let's have a look on the back side. Go back again. I think this is a very cool feature. I really like that a lot. Okay, now we have the design, and I'll generate the Gerber files, send them to production at PCBWay, and then let's have a look on the produced board. And here the PCBs from PCBWay arrived. Let's have a look. They are not very big, these PCBs, only 30 by 30 millimeters in size. Let's have a look on the quality here. Look like, yeah, perfect. And you see the footprint there for the MCU, it's very small. But all 8 pads are there on the back side. I'm really looking forward to this. Let's hook up the hot plate and see if we can solder some MCUs to this PCB. So for the soldering, I'll use a couple of tools. One of them is this mini hot plate that I bought from PCBWay, and you can find the link down in the description down below. This is a very nifty device for this project, I think. So the hot plate itself only measures 50 times 50 millimeters here. It's just a protective cover, a small display and some buttons. And here you have the power ports. You can either power it from USB-C or from a DC power jack. And the maximum consumption from USB port is 100 watts, and from the DC port it's 150 watts. Some other tools that are necessary. I have this AMTECH Flux here that I bought from Northridge Fix. You can also find the link down below. This is a flux that will protect the soldering process. And of course some fine tweezers as well. And from Texas Instruments I bought the chips themselves. I got these pre-production devices here, 10 pieces. Let's hope we are able to solder it with success. So here we have the PCB under my microscope, and the first thing to do is to apply some of the AMTECH flux. This will protect the soldering process. And here I'll try to put the MCU in place. It's a bit of a fiddly task. This is very small dimensions, and I just made the video go a bit faster here because it's a quite tedious process. So now I'm close to be satisfied with the position of the device. And we are now ready to start up the hot plate. This will heat up the board to 230 degrees in different steps, so you can follow the temperature here on the display. And you see now some of the flux will start to melt. And I think in around 210 degrees or something, then the MCU will be dragged in place. But let's have a look on what happens. So now we are at 170 degrees. And there you have it. You saw that the MCU moved a bit and it was dragged in place. I'll also just show you a couple of other boards that I soldered with success. In total I made 5 boards and all of them was soldered 100% and they are fully functional. So I think this is possible to do at home, even though we are talking about very small dimensions here. And this is board number 3 that I was experimenting with. You see there's a bit less flux on this one. That it moved in place. And I think we have a last one as well. And when the temperature reaches about the 210 degrees, then the reflow will happen, and there you had it. So this video is sponsored by PCBWay, who offer a wide range of manufacturing services for your projects, including PCBs from very low-cost prototype boards to more advanced PCBs, all the way up to 60 layers, and also with specialist FR4 materials. You can also get your rigid flex PCBs made if you want to make something a little bit more interesting. They also offer a wide range of PCB assembly options. That means getting your PCBs assembled with components on both sides of the board, whether they be surface mount or through-hole parts. PCBWay also offers some mechanical services such as CNC machining, sheet metal fabrication, 3D printing, and also when you're making something with a little bit higher volume, you can also get some injection molding done here. So don't forget to visit PCBWay.com. So now we have the PCB, it has cooled down, and let's try and check if the pins are soldered correctly to the board. So we can test some of the protection diodes inside the MCU. They are connected directly to these pins here, and we can just verify that by measuring from the minus side to the GPIO pin. So let's check that pair of diodes from ground to the GPIO pin. And we can measure there are some diodes here. And then ground is of course a short circuit. And then we can go from ground to the GPIO, or then we can go from the GPIO pin to the VCC or the 3.3 volts. And let's try and check that as well. It looks fine. And there should be a short circuit here because that's the 3.3 volts. And then the last two pins here, you see there's no connection. And that's because the last two GPIOs here, they are open collector. So they are not connected to the 3.3 volt side. So now we have verified that the MCU is soldered correctly. Let's solder some parts to the board, the remaining parts. And then let's try and see if we can get some code downloaded into this board. So for programming our custom board, I bought this Launchpad SVD programmer. So this is basically a device programming a for programming our custom board, I bought this launchpad module specifically made for the MSPM0C1104 family. So this is basically an SVD programmer, and over here we have a target MCU. So if we remove these jumpers, we can isolate the target here, and then we can feed the signals directly into our custom board. So I bought this from the Texas Instruments web shop, and the price was only $5.99. So this is really a cheap price for this programmer. Let's try and hook it up to one of our boards and see if we can connect to it. For the programming of our custom board, I bought this launchpad module from Texas Instruments. So this is specifically made for the MSPM0 C1104 family. So we have here the SVD programmer, and we have the target MCU here. There are some buttons, and there's the USB interface, and there are some LEDs as well. You can see here we have all the needed signals for the programming. We have 3.3 volts, we have a reset signal, and we have the SVD port. So if we remove these jumpers, then we can directly connect the SVD programmer to our custom board. So I bought this from the Texas Instruments web shop, and the price was really cheap. The price was $5.99. So let's try and hook it up to our custom board and see if we can program our devices. So here we have the Code Composer Studio from Texas Instruments. This is a free of charge program you can download from the Texas Instruments homepage. And yeah, the first program we have is of course a small program that will blink the LED. This is just for verification of the functionality of this. So let's try and download the program. Start debugging. And now it will transfer the program via the SVD line to the board. And let's execute the program. And now we see that the LED is blinking with a slow pace. Just for fun, we can just try and increase the blink speed. Let's try and debug this and transfer the program. And then continue here. And now we see that the speed is increased. So I made a bit more advanced program, a small thermostat. It consists of a SI7021 temperature and humidity sensor and a very advanced display from SparkFun, a alphanumeric display. So I will connect that to the quick connector, and I will show you the software in a second. So here we have our thermostat program. I have connected an SI7021 temperature and humidity sensor and a display. And it's connected via the quick connector. So we have some routines here for reading out the humidity and temperature sensor. And we have some code for writing commands to the display. And then we have some helper functionalities here for sending out the numbers to the display. And then here we have our main program. We initialize the display. And then we read out the temperature and the humidity. And we display the temperature in the display. And also if the temperature is more than 30 degrees, then we will turn on the PA24, the yellow LED. So let's try and see what happens if we put our finger on the temperature and humidity sensor. And here we have the display. As you see right now, the temperature is 23.7 degrees and the yellow LED here is off. So let's try and touch the temperature sensor here, and we see that the temperature goes up. And when we hit 30 degrees, then the yellow LED turns on. and if we go below 30 degrees it turns off again. So this is quite cool. This is controlled by this very small MCU, and it was quite easy to program. So there you have it. We designed a board, wrote firmware, soldered the world's smallest MCU, and tested it in action. If you enjoyed this deep dive, don't forget to like, subscribe, and drop a comment below with your thoughts. Would you try working with the MSPM0C1104? Let me know. Thanks for watching, and I'll see you in the next one. Bye.